Good morning, Mr. Leshuvs here. We are carrying on with our investigation of graphs, and we're using first and second derivatives to analyze graphs. Actually, what I'm going to tell you now, I think we kind of did it, but maybe giving it a little bit more emphasis here. We're looking at stationary points. Okay? So we looked at three kinds of stationary points. Okay? What would we call this kind of stationary point? This one.
Concave down.
It's a?
Okay,
let me give you the words. Right. So we have local minimum, local maximum, and what do we call it?
Marcus, local.
A stationary point of inflection.
Local
So what is that?
Local maximum.
Local maximum. Great. So that's a local maximum, meaning this is a local minimum. And this one, we said it's a stationary point, which is also a point of inflection, right? How do they want to call it? Stationary point of inflection. Okay? Stationary point of inflection. Okay? We'll put some details on this. Now, what is true for every stationary point in terms of the derivative? What is the derivative equal to? Zero. In all these cases, the derivative is zero. All of the derivatives is zero. Okay, that's like the definition of the stationary point. The tangent at this point will be horizontal. Okay? Right. The question is, how can we tell the difference? If all of them have the same first derivative, how can we tell which one is which? Obviously, if I see the graph, I can see that's a local maximum. But if I don't see the graph, if I just have a function, I'll draw the function that we're going to look at a second. So I'm going to have a function f of x equal x cubed, or minus x cubed, plus 6x squared, and minus 9x plus 3. Okay, so that's the function we're going to work in a second, and we're going to try and find all the stationary points and then classify them, which one is which. Okay, so to figure out what is the local maximum, we have to look at the second derivative. Okay, and what do you think will be the second derivative?
Well, that's obviously in terms of zero.
Is it going to be zero, negative, or positive are the answers? And you don't know right now, because I haven't taught you that. But what I did teach you is about concavity, remember?
Down.
Okay? This one, as you say, JD, is concave down, right?
Smaller than
This one is concave up.
will be smaller than
Okay?
zero.
So you're right, JD. Because the local maximum is always concave down, that means it is negative. Yes, I want to just make sure that you're right. Okay? Yes, you're right. So if you look at the notes from last lesson, concave down means the second derivative is negative. So if you check out the first derivative is zero, okay, we know it's a stationary point. Now you check the second derivative. If it's negative, you know it's a local maximum. Okay? Where if the second, what will be the case if we have a local minimum? What will be the second derivative? Larger than zero, because this is concave up. Do you understand? Okay? Now, I call it stationary point of inflection. Okay? Remember what we said this point of inflection is when we have a transition between concave down to concave up. Obviously, we could have the opposite situation. We can have a concave up to concave down. But in both cases, what will be the second derivative? Okay, what is the necessary condition for a point of inflection? What should be the second derivative equal to? Zero. It must be zero. Okay? So guys, these are the conditions for the type of stationary point. Okay? If you have a local maximum, or first of all, or for any stationary point, the first derivative must be zero. If the second derivative is negative, that's a local maximum. If the second derivative max is positive, therefore it's a local minimum. If the second derivative is zero, and there will be a point of inflection. It's a suspected point of inflection, but we'll call it just point of inflection. Okay? We happy with that? All right. So what are they asking? I'll just pause here for a second. Okay. All right. So I'm actually making the question they gave us a little bit harder. So they give us this function, and what I want us to do is find the stationary points, and then classify them. Classify me. Is it the local maximum, local minimum, or is it the stationary point of inflection? So what is the first thing we should do? Find the derivative, okay? And remember, find the derivative just for any x. So what will be, I'll let you help me this time, okay? What will be the first derivative? Minus 3x to the power 2 plus 12, yeah, you're right. Plus 12x minus 9, okay? Now what do I have to do with this minus 3x squared plus 12x minus 9? What should I do with it? Before. I want to find the stationary points. What's true for all stationary points? The first derivative is 0. So must I do that equal to? 0. Must equal to 0. So if you lost in the calculus question, first you find the first derivative, and you still lost, make it equal to 0, solve for x. Okay? Alright. What do you reckon should we do here? Divide by minus 3, I would say. Okay? So it's going to be x squared minus 4x plus 3 equal to 0. We can see that it's x minus 3, x minus 1. So we found the two stationary points. Can you still see here? Okay? There's two stationary points in x equal 1 and x equal 3. Okay? But at this point, I don't know what kind of stationary points they are, right? Right? Before I find what stationary points they are, let's try and find out their y's. How do I know what the y when x is equal 1? Plug in where? In the original function. Okay? So I'm going to just save us some time. If you plug 1 here, you will get minus 1. And if you plug 3 there, you will get 3. You get 3. So both points are 1 minus 1, and the second point is, I'll write it down here, 1 minus 1 and 3. But at this point we don't know which one, what are they? Are they maximum, minimum, maybe they're point of inflection? How would we find out? What do we need to do now? Going back to what Oli said, I think. Find the second derivative. Okay? So we find the second derivative. What will this be? Minus 6x plus 12. Okay, how does that help me now? I'm going to write down here, I ran out of space. Okay, so what do I do now? I've got the second derivative. What should I do with it?
See if it's possible.
Okay, so, but what do you mean? I mean, I've got an x. I don't know what x is. What do I do?
0.
X equals 0?
No.
Plug what? Okay? So we plug the x of both points. Okay? So we're going to find the second derivative when x equal 1. I'm plugging in 1. We're going to get minus 6 times 1 plus 12, which is 6, which is larger than 0, right?
Yes.
Okay, what does that tell us about this point? What is 1 minus 1 if it's larger than 0?
It's local minimum.
Local minimum. Okay? Local minimum. Okay? So this one is a local minimum.
So I just wanna.
Yeah, I know, let me just pause. Alright, so now we want to find out the nature of this point. So I'm going to sub 3 in the second derivative. Minus 6 times 3 plus 12. And that's equal to minus 6, which is smaller than 0. Just check me, right? Okay, so what is that if it's smaller than 0? It's a local maximum. And then we're done. Okay? Alright? Let me just see if there's anything else. I'll say goodbye here. Let's work.